So a couple of key things happen. So when gas is that hot, there's we talk about the states of matter. You have solids where ice, it's cold. The atoms are now bound in a lattice structure together. They're held together. And then liquid, you've broken a lot of that lattice structure. They can move around. They have some kinetic energy, but they're still pretty contained. They stay in the bowl. Keep heating it. Now you're in gas. And now these particles are free to move around. They're moving around. They're bouncing off of each other all the time. And you can keep heating it from there. And that's where we talk about some more phases of matter. We can add a little bit more physics here. We talk about rarefied gases. So when we think about most gases that humans interact with, they act like a fluid. And what I mean by that is that they're colliding with each other so often that the particles at any one place here, the air is roughly the same temperature as the air here. That these particles are bouncing off of each other. If you put a really hot one right here, it would then cool enough that all the air is roughly on the same temperature. But you can be what's called rarefied. And this is like space. This is where now you have particles moving around, but they don't collide with each other very often. And so you can have one very, very high energy particle and very cold energy particle, and they may not even touch each other, but maybe occasionally they bang into each other, they collide, and then they transfer energy. And that's where we call rarefied. And then you can go even hotter than that. And that's where now the actual atomic states, which has the nucleus, which is a proton and a neutron, and an electron gets so hot that electron gets energized and then escapes, leaves the system. And now they're charged. You have a positive nucleus and a negative electron floating out. And that happens on the order of 10,000 degrees. So way hotter than what we're used to. But now we're going to go hotter. We're going to take this plasma and go even hotter. And what does that mean? At that point, a lot of the way we think about temperature doesn't really apply. The idea that you have these random motion of particles, because now they're all individual particles moving at very high velocity. So what it's really is a measurement of is velocity. It's really a measurement of how fast is that particle moving. And that's how I really think about temperature when you get to that 100 million degrees. And so it does some more complex things. If you have this high energy particle, that's why we like fusion, is moving at high velocity, and there's another one moving at high velocity, they will come together, they will collide, and they will fuse. Mm-hmm. But other things will happen. You don't want to touch that high velocity particle with any kind of material, because it will collide with that material, damage that material, and usually like blow off some chunks of that material. Mm-hmm. So we don't do that. We keep those charged particles in a magnetic field. So they just bounce around and they don't ever touch anything. And that's really important. And so it's less thinking about it from the way we normally think about hot and cold, and more thinking about it from a velocity point of view.
So what we should be imagining is extremely fast moving. What is it? 1 million miles per hour? Is that accurate?
That's the right kind of order for these systems.
Crazy.